Welcome to this presentation, or there are two presentations, basically the same name, but we will look at first one will cover erosion effects on the bentonite barrier, and the other one on mechanical performance. BELBAR was a collaborative project within the 7th framework, and the main aim of BELBAR was to increase knowledge on the processes that control clay colloid stability, generation, and its ability to transport radionuclides. The overall purpose was to come up with a new way, or at least an improved way, of treating these issues in long-term safety assessments, performance assessment. BELBAR started in March 2012 and ended in February 2016. So this is a few years ago now. The project had 14 partners from 7 European countries. You see the organizations represented here, and this is on the map. What did we study? And this, I think, this image is the overview of the project. Basically, we have a waste canister. Could be any, that doesn't really matter which material it is, a bentonite barrier surrounding it, and a fractured rock. This problem with bentonite colloids is actually only a problem in a combination of a bentonite barrier and a fractured rock. In a clay or a sedimentary host rock, this is a non-issue, so that's why we have the countries that were represented. What can happen then? Under certain conditions, bentonite can form colloids. Bentonite first penetrates into fracture, it forms colloids, and the colloids can be transported away with the flowing water, which means a loss of a barrier. These colloids could, if the canister is broken, also possibly carrying radionuclide, which means that radionuclides could be transported faster because they would sorb to the bentonite colloids instead of the host rock. The structure of the BELBAR project was that it was driven by the safety assessment, so all the results, the arrows started in the other direction when we started the project, but we wanted to get feedback to safety assessments. A key thing is colloid stability. When are colloids stable? And stable in this respect means a bad thing. Normally, stable is good, but if the colloids are stable, they can carry nuclides and they can erode the barrier. We had work package 2, erosion, which is dependent on colloid stability. We have radionuclide and host rock interaction, which is dependent if you have erosion. This can only occur if the bentonite is eroding. To represent this in safety assessment, we need conceptual and mathematical models, and then we have safety assessment. I will focus on these 3 work packages in this presentation because we basically have limited time, and that's where most of the scientific work was actually done. Work package 4 then. What did we do there? Looked at clay colloid stability under different geochemical conditions. We tried to find reasons why different clays behave different. Critical coagulation concentration is the measurement on which groundwater composition or salinity you need to destabilize colloids, and when can this happen. And then we also looked at the role of complexing agent. Can anions or complexing agent actually stabilize colloids? The theory behind this is that you have different phases of the bentonite. In the deposition hole, you know the bentonite is swelling, which here is represented, we call it a repulsive paste, or possibly sometimes it's called repulsive gel. If the salinity, here expressed as sodium chloride concentration, is sufficiently high, we form instead an attractive gel, which holds together. But if with the decrease in clay concentration, as long as the clay concentration is high, it will always be swelling, but that swelling either stops as an attractive gel or it forms a sol, which basically is liquid. And if you look at this in the deposition hole, you have a buffer with the expanding clay you form a sol or a gel, and the sol can be transported away with the seeping water. This is hardly difficult to see because it's not very clear, but this is the different phases for two different bentonites, one Indian and one Wyoming. If you manage to see the scale, you can see that the Indian clay is stable at lower concentrations. And the conclusion is it seems like clays having more charge located in the tetrahedral layer form larger colloid, and these sediments easier and it's more stable. Role of cations. This is an experiment with different cation concentration. We already knew in the beginning that monovalent anions form more stable colloids than heavier monovalent anions, and divalent anions doesn't form colloids as easy. Stability above a critical coagulation concentration, which is maybe 4 millimolar sodium chloride for a mixed clay, sodium calcium, and 25 millimolar for a pure sodium clay. You form a gel and no colloids are generated. This CCC varies among sodium montmorillites of different origins. Calcium montmorillite does not form colloids. However, only 20% sodium is sufficient to basically turn a calcium bentonite into a sodium bentonite in this respect. When it comes to swelling, we know that this is basically the opposite, and then it behaves like a calcium bentonite until you have about 80% or at least 50% sodium. Anions have a minor effect. Organics, if we have organics in the system, maybe for high-level waste this is not so important, they can stabilize colloids, making things worse. The attractive forces, they increase with aging. This is basically a little test tube where we had formed a very loose gel. We tilted the jar, let it stand for 2 years, nothing happens. So a gel is, when you get to this non-swelling, non-expanding gel, it is stable. Work package 2, erosion. Then that's dependent on the bentonite clay, the groundwater chemistry, the groundwater clay interaction, and that is how you model it in the safety case, the groundwater velocity, and the clay extrusion path, and the fracture geometries. What do the fractures actually look like? And different types of experiments were employed, like static experiments where colloids are formed in a filter. You can do the same thing, but you have a dynamic system where you pump. What was not invented in this project, but very much used, was artificial fractures, which actually mimic a real deposition hole, where you have a flow and you can catch the colloids. This is a cartoon, and this is how it looks in the reality. You have a camera on top, you pump a flow, and you collect the clay. The results from these flow experiments, it was a large number of experiments performed with different concentrations, always below the CCC, otherwise you don't form colloids. The average mass loss seemed to be slightly correlated to the flow rate. We thought that it would be a function of the flow rate because it's an erosion process, and you see here for certain experiments you can find a trend somewhat, but you have 4 orders of magnitude here and less than 1 order of magnitude here. So it's not a very strong dependence on the flow rate. And the observed variability is generally about the same order of magnitude as the flow rate. In other cases, water flow doesn't seem to be a relevant or important parameter at all. Very surprising results, because when we think about erosion, it's flow dependent, but it seemed like this is not the case. We did to see this. Another uncertainty factor is actually how you perform the experiment. So we did the benchmark, which started with stagnant conditions in one of those cells I showed you before, and the extrusion distance was measured. Then you had a low flow condition for 14 days and what we call a high flow conditions, 1 micrometer per day and 0.1 millimeter, or a micron per second or 0.1 millimeter per second. And we measured the effluent. When you look at the pictures, these are from 3 different labs. Some of them have more data than the others, but you have the circles, the triangles, and the squares. You see the extrusion distance coincided quite well, at least between the triangles and the circles. The squares came a little lower. Interesting, we can see that you get this when you turn on the flow. Here is the stagnant system. You basically have colloids outside. But in the flowing system, you form this amoeba-shaped phase. And when you increase the flow, this amoeba breaks up and travels away as something that is not the colloidal phase, but more a flock phase. We had the results from 3 different countries. They performed the experiments with slightly different geometries. What is interesting to see that when you get to the lost mass, it seems to be very country specific. Erosion is much less pronounced in Spain and much more in Scotland. So there is definitely an operator issue here when you compare experiments that even though they tried to do identical experiments. The extruded mass, they got fairly the same. So it's radionuclide and host rock interaction is a different issue than what are the colloid mobility processes? Is sorption reversible? And that is the key issue here. Is sorption, if it is reversible, then this will be a small factor because the rock, it will sorb on the rock anyway. If it's not, and can we see why do we observe kinetics? And are the other retention processes occurring? This is a complicated experiment, basically shows that this is a slow release of, it's europium on bentonite, and the europium with increased equilibrium time, the kinetics is slower, but independent of equilibrium time, it seems like all equilibration time, you all go back to the same sorption value, which basically shows that we have reversibility in all cases for trivalent anions. Conclusions overall from this project. Understanding of bentonite colloid stability was largely confirmed, which we hoped that the hope would be that we could see that the colloids are less stable than we anticipated in the past, but basically colloids form if the water is sufficiently dilute, and that's basically a fact. This is difficult to avoid than in crystalline rocks. Independent, we first thought about it as situation for glacial meltwaters, but these waters have been observed like in other countries, like in Spain and the Czech Republic. If you have enough rainwater, you get the diluted water even at depth. The erosion, I didn't talk about the modeling. The erosion process is difficult to describe, and we have big problems. We have continued to work with this after this project, and we have big problems describing it both conceptually and mathematically. Something that I didn't mention in the presentation that we didn't discuss when we proposed the project was the effect of gravity, because we thought that gravity shouldn't have an effect on colloids. It definitely did, and it's quite strong, and we don't have neither a physical understanding nor a possibility to model this. The interesting thing, though, it seems to be the gravitational effect coincides with CCC. So if no colloids are generated in a flowing system or a stagnant system, there's no effect of gravity either. Reversibility of radionuclide sorption onto colloids was largely confirmed, basically for every single radio element, possible exception of pentavalent actinides where it's not as clear, but as plutonium-5. Depending on the flow conditions, though, you may have to look at kinetics in the safety assessment, but most cases kinetics is faster than the times we have for transport, so we could probably get away saying that we can assume full reversibility. And thank you very much for this presentation about the Bell-Bar project. Now we'll talk about totally different, still bentonite, but something completely different. The mechanical evolution effects on the long-term performance of the bentonite barrier. This is an overview of radioactive waste disposal. You all know that we want to have geological disposal is the preferred option. We want to have a multi-barrier concept. Waste form, a container, a filth or material between the container and the geological formation, and I'm going to talk about this barrier, which commonly is referred to as a buffer or backfill. We'll get into more issues on that. Why do we have bentonite? We want to have a diffusional barrier, basically that diffusion should dominate over advection as a transport process. We want this barrier, as I said, for the Bell-Bar project, you don't want to lose it through erosion. You will have a maintained thickness. You want a self-sealing ability. You want physical and chemical stability in the long term. You want to minimize microbial activity, and you want the colloid filters. You want the barrier to be there. But if you look at this, yeah, and these are typical disposal concepts. This is the KBS-free concept with the copper canister, vertical borehole surrounded by bentonite. This is the Nagra concept for opalinous clay, where you have steel canister on a bentonite pedestal of compacted blocks surrounded by pellets. It's bentonite barriers in both cases. We can also have, like in the French concept, bentonite is not used as a barrier surrounding the waste, but it's still used in seals to seal the tunnels. So it can have many uses in different ways. In low and intermediate level waste, bentonite can also be used. Why mechanics then? Because all the processes I talked about were basically hydraulics. And it's not so much heard about bentonite mechanics within the radioactive waste community in the past. So why do we bring it up now? The reason here is that we have engineers as well in this business, and they want to be able to emplace this. And this is very much is that when you have installed the bentonite, you may have gaps, hole, in inhomogeneities, in density distribution in the installed material. And this is caused by especially very heterogeneous initial conditions caused by installation technique. You will have blocks with gaps between them. They will never be tightly together. You will have gaps filled with pellets or open. You will have mechanical interactions in the system. In KBS-free system, we have a buffer and a backfill that will interact with each other. You may have backfills and plugs that push each other one way or the other. You may have other things. You may lose bentonite in a deposition hole or in a backfill tunnel or in a plug by piping in erosion during the installation phase when you have high gradients, by colloid erosion like I talked about in the previous talk. And then the question is, how well can the bentonite self-seal and homogenize these anomalies? And that is the question then. And to understand this, we need to develop and calibrate and verify material models and modeling techniques to be able to describe this, so we have the initial conditions for the safety assessment. And this is the view. This is a KBS-free disposal tunnel. When you, at least from our application, if you construct a tunnel with drill and blast, this is seen from the top. You drill, you blast, and then you have this shape seen from the top. And you fill 1 tunnel diameter. On the narrow point, you have a lot of blocks. On the wide point, you don't have that. But in the safety assessment, we just say, oh, this is a backfill with a given homogeneous density. this is an optimistic approach. This is very rare that we use this in the long-term assessments. And so mechanics is important. Then the key issue here, can we justify the dry density approach? We have pellets, voids, blocks, sometimes very complex, or quite often very complex geometries, like in the Nagra case, the Andra tunnel plugs. They have complex geometries. This is and you may have bentonite, as I said, the expansion out of deposition holes. As I said, you will have erosion. We can have installation failures as well. And this is a picture of how a real system looks. This is not a homogeneous density. So the question here, can we justify this approach? This works, when we initiated this project, we thought that this works very well as a joint project because this question is totally independent of host rock. It's totally independent of waste form. It's totally independent of waste canister. The only thing is that if you have bentonite in your system, so if you have a system like the Belgium one where you rely on concrete and then maybe this is not an issue. But if you have bentonite as buffers or seals, it's all common. The issue is exactly the same in all the programs. The conclusions may be different from the modeling, but you need the same tools. And that's why we started Beacon. It's running from, it's a part of Horizon 2020. It runs from 2017 and to 2021. We're exactly at halfway now. And the objective here is to develop and test the tools necessary for the assessment of mechanical evolution of an installed bentonite barrier and possibly the resulting performance of this barrier. And why do we need this? This is to verify the performance of the current designs. This is a question that is sort of in between engineering and long-term performance, and maybe that's why we haven't given it so much attention in the past, because the engineers think that this is an issue for the safety assessment, and the safety assessment say, oh, this is an issue for the engineers. And if you have a long time to implementation, then you can probably think that way. But I think that both from SKB and Andra felt that when we're getting closer now, we can't just say that this will be a perfectly homogeneous system. We hope that we still can claim this after the project, that this was an okay approach. And so we can verify the design. So Beacon then, the end will be to directly application to real assessment cases in actual repository systems. And we have cases from relevant repository systems, and we'll get back to that. We have 5 technical work packages, which is work package 1 is the safety assessment part, actually defines the cases and takes back the results. Work package 2, I will get back into more detail on this, is there's a lot of experimental data available, but we say we haven't dealt with this. No, but the experiments are still there because all the large field scale experiments actually have been installed this way. So, and we have done laboratory experiments, but they have never been, or they have only to a small degree been evaluated on the mechanical performance. It's often either demonstration or we're looking at water uptake or other issues, but the data is there, but it's not been evaluated. And so there's a large database. Model development is crucial. Antonio is leading this work package. Do we have the correct tools? Do we need to improve them? Lab testing, we have a rather, compared to many other projects, the experimental part of Beacon is quite small. We say we'll have no large-scale experiment since we already have the database. We only engage laboratories which have quite a bit of skill and can quickly respond to needs from modelers. We have a rather flexible experimental program. No experiments with long running times will be allowed in the project because we can't use the data. So it's only short-term experiment to determine critical parameters. And then we have the whole key work package in and that's work package 5, where we actually do testing, verification, and validation of models. And this is the core of the project. And this also feeds back into the assessment cases will be performed here, but they will be evaluated then eventually in the end of the project by work package 1. And we have 25 partners from 10 countries representing 9 national programs. Work package 1 is to define the needs of safety assessment. We also, I think this is the old, okay, presentation, but anyway. Work package 1 was compiled to answer a questionnaire. The questionnaire aimed at reflecting the state of the art regarding the treatment of heterogeneous bentonite, density distribution and properties in the safety case. And based on the outcome of the assessment cases, we can evaluate then how good are the tools. At this stage, we have a published NAGRA report which answers the questionnaire, application of the bentonite in specific design from the different programs, the required performance, and detailed characterization of the required properties of the bentonite. Work package 2 had 3 tasks. A workshop that was basically the first kick-off meeting where we had discussed the relevant national the information available. And task 2.2, which was identification of the relevant data and the models, which is the core then of work package 2. This was managed by Simon Norris, and this has also been completed, and then the last task is to identify how has this improved. And the work package 2 is an extensive database of the available information, and I think this is not just helpful for the project as such, because here is a vast database that people entering this field can directly go into this and see what is available, what has already been done, what do we know, and it's collected in one place with quite good summaries, data sheets of what was done, and also all the references to the original documentation. Work package 3 focuses on the mechanical constitutive models, and there's a lot of issues that need to be covered, reversibility in the stress path, and the difference here is that the models are sometimes available, but the focus on the past have been on thermal and hydraulic properties as the primary focus. If you look at PEBS, for example, which was a predecessor to Beacon, where the TH process were the dominant ones. And you should be able to consider saturated, unsaturated material, compacted blocks and pellet-based, isothermal and non-isothermal condition, and this needs to be implemented in computer codes capable of performing coupled HM and TH analysis. Objective of work package 4 is laboratory testing. As I said, small-scale laboratory experiments that will provide input data and parameters for development of validation of models and to reduce uncertainties about certain phenomena. Basically, sometimes we don't know, should this be included in the model or should this not be included in the model? And then you can, if you have some tailor-made experiments, this can be resolved. This is an example of a typical experiment where we look at a mixture of a system consisting of bentonite block and bentonite pellets measuring stress, and you can determine the final dry density profile. So this is the initial dry density profile, and then you see that you get homogenization after the test has been run. This is then the strategy and for work package 5, but also the strategy for the entire project. And our idea then was to start with test cases with different objectives and different degrees of complexity. And the first one then should be verification, validation cases, test with simple physics, test with coupled processes. And this is task then 5.1, very well instrumented laboratory test, which initially should be quite simple, at least from boundary conditions and geometry. The second is then large-scale experiments, available field-scale experiments where we already have the data. The tests here that have been selected are FEBEX from Grimsel. We have selected the EB from the Monterey Underground Laboratory and the canister retrieval test from ESPE because they were found to be the ones that were most suitable for this type of modeling. This task is ongoing for the moment. This one has been concluded. The next step then is to do predictive simulations on laboratory tests going on that will be concluded in work package 4. And we have to decide based on the outcome of the two first one, which to select here. And the last is assessment cases. And here we, prior to the project, we already selected the Andra tunnel plug, the Nagra disposal cell, and the KBS-free deposition tunnel backfill. These are different cases. It's from Free National Program, but they should be representative of basically every single problem in this business. So it's not just solving problems for free organization. These are general enough that if the model works here, it should work on any problem. So it's just that we wanted cases that are real so we can test the capabilities of the models. This, I unfortunately uploaded a newer version of this one, but this isn't. This test, we were a little naive when we selected this test because we thought it was very simple. What it actually is an odometer. You have a 50 millimeter height and you put in a 100 millimeter diameter. We put in a bentonite specimen that is 40 millimeters high, so you have a void that's 10 millimeters high. And you add water. This system was actually flooded, so you don't have to think about the saturation process. And the bentonite expands, and here we have the axial stress measured, and we have the radial stress in 3 points. You can see that we don't get to full homogenization, but the stresses increase and very quickly here, and then of course the bentonite expand and it decreases in the bottom and the middle radial. And we thought that this is simple, but goes very different. This is the number of, this is from last year's meeting, so it should be filled in as well. So we had a number of teams with different models that looked at this. The test I show here is the test 1A02. And so there was a number of groups trying to model this. This is the measured result of the axial pressure. And these are the model ones. You can see one is going up there through the ceiling, and the other ones are. So this was not so easy. This was actually very challenging. And Antonio or Liliana can explain to why it's so difficult. But my feeling is that when the bentonite hits the ceiling in the cell, it changes from expanding to contracting, and numerically this is challenging. And the main comment stem from this is that we can get the general trend well represented. The voids introduces new difficulties. It's difficult to get the pressure evolution, the void ratio, and water content. The transient phases are difficult to catch. Collapse during saturation or underestimated in many cases. Do we need to consider hysteresis? Selection of material parameters. We found that we need to check why people got so different results. Role of friction in small tests. We have walls. We know now from, because we had a meeting just before this meeting where we got new results that unfortunately wasn't included in this presentation that was shown here. It's still on the website, I think. Okay. and there are some uncertainties, sometimes difficult to identify how was the experiment performed, and need some exchange between modelers and experimentalists. I think that was work package 6. Yeah, Christophe talked about civil society. Civil society is included in the work package here to discuss and give feedback, and maybe the feedback here was sort of misinterpreted by, wasn't a review. The idea was to translate scientific results in a project like this. This also found to be, in modern 2020, it's probably easier because you have a real case that is understandable. This is a very tricky, it's been some problems here, and to enhance the possibility of interaction with civil society. I will go back a little quickly because one slide was to this slide. We have progressed further here, but our last meeting was just before this meeting, so it was unfortunately not included in this particular presentation. As I said, there is a newer one where a little more is included. We are here, have performed all the task 1 tests now, and it looks totally different. The modeling results of the continuation of the small-scale test give much better results, and that is 2 reasons, or 2 possible reasons. One reason is that those tests were simpler, but maybe more that people have actually learned from each other and they have improved their models, and I think that is more the reason here. Christophe talked about training. Yesterday, the importance of training. We had a training course. Feedback from earlier projects is that you should have a training course early in the project, especially for people involved in the project, because then you get quicker up your knowledge levels. We tried to have it the very first year. We did so. It was very successful, maybe a little too successful, because Antonio, that hosted the course, had problem finding a room large enough for all the students who wanted to take this. We thought that who is interested in mechanical modeling of bentonite, but it was a huge number of people that wanted to take this course. But this is not the only training. We had 36 or something like that. We planned for 20. So that was, and yeah. And I think that, but we had 5 professors from different institutes giving lectures. So of course, there's nothing that you could get anywhere else. But we have another training component here that I think has been even more important, that, as I showed you the number of teams that have been involved. Of these, maybe 2 or 3 had actually done mechanical modeling of this bentonite before in real assessment cases. A few of them had the tools, but they had not really tested them. And the other ones had ideas how to do it, but sort of not gotten further than that. And now we're halfway through the project, and I would say we have maybe 10 teams in Europe that can model these type of cases. So going from 2 to 3 to 10 that are capable of resolving these type of issues. Still on the learning curve, but we can at least know that we have, and it's not just the information, or sort of the training has not just gone from developed to less developed, but it also goes the other way around, because people come up with new ideas. I think, Antonio, you can confirm this, that can be used of the more developed programs. So this project has been very successful in the way we focus on a very small single issue, and people work together on, not together with their own experiments comparing, but on exactly the same topics and learn from each other. So my feeling is that we have made very strong progress so far in just 2 years, and we actually have quite a bit of results. From work package 3 is also been published a state-of-the-art report that shows the models available, which is something that would never have been done. And for new people coming into the business, they can definitely go straight into this one and see what is available. Thank you very much for your attention.